Let's check it. This is not important. For 2 years now.
No, I think it looks
new. I think it's
no, it even looks new. I think it wasn't here when I came this morning. So.
Put some water here too.
Yeah. It was somewhere else for a month.
Thanks.
Yep.
בוקר טוב לכולם. I'll do part in the Hebrew, part in English, so apologies. ברוכים הבאים לטקס שנתי לחלוקת פרס בנטו ולהרצאת בנטו. הפרס וההרצאה מתקיימים מדי שנה בתרומתה של פרופסור מרים קסטנר, שמחפש לו מקום לשבת כמובן. שיצרה לנו מסורת מאוד מאוד מכובדת ומרשימה, גם של זוכים וגם של מרצים מחו"ל. ואני רוצה לציין שהשנה מרים גם הודיעה על בניית קרן שתמשיך את מתן הפרס באירוע לשנים רבות מאוד לעתיד. אז תודה לי. בחלוקת הפרס, נתחיל בחלוקת הפרס, אחרי זה כמה דברים על פרופסור יעקב פרדיקטור. ארי, נכון?
אקריא את נימוקי ועדת הפרס. חתן הפרס הוא עידו סירוטה. הוועדה דנה בשני מועמדים מצוינים, בחרה בעידו סירוטה מהנימוקים הבאים. מחקרו של עידו התמקד בדינמיקה בזמן ובמרחב של הפרדת משקעי מלח, תצפיות בים המלח והשלכות להבנת משקעים אבפוריטיים. המחקר הזה הוא חדשני, הוא פורץ דרך. עידו הציג תיעוד נדיר ומפורט של הצטברות משקעי מלח בקרקעית האגם במהלך העונות השונות וכתלות בעומק. תצפיות כוללות התייחסות למצב הלימנולוגי של האגם ולמאפיינים של המשקעים, כגון גודל דרגה ושאר מאפיינים טופוגרפיים. מכאן פיתח עידו מפתח חשוב ביותר לפענוח משקעי מלח בעבר, באגן ים המלח ובעבר הגיאולוגי במקומות אחרים, ולקשר בין אופי המשקעים לתנאים הסביבתיים. עידו גם עסק באופן כמותי בתהליך המרכוז של משקעי המלח, להבנה זו השלכות רחבות בפענוח ופרשנות של משקעי מלח עבים, כגון כמה מים צריך להדות מעל אגן היפרסליני כדי לקבל אופי מלח מסוים. מחקר זה מהווה דוגמה נפלאה לעיקרון של ההווה מפתח לעבר. כיום כבר משתמשים במודל שיצר עידו להבנת משקעי מלח העבים במסיניאן של הים התיכון. בפרק זמן קצר פרסם עידו 3 מאמרים חשובים ב-Water Research, ב-Geological Society of American Bulletin וב-Geology. הישגיו אלו אנחנו מעניקים לעודד פרס בנטור בשנת 2000. עידו.
עודד קיבל פעם.
עודד כבר קיבל.
עודד ועידו בתנ"ך יש אומרים שזה אותו בן אדם.
פה זה לא, פה זה לא.
אז אני אגיש ייקח לעידו בסיבותה, בפרס בנטור לשנת 2018. עידו?
ועדת הפרס, תודה רבה, שמרים קסלר שתורמת את הפרס ובעצם מאפשרת את נתינת פרס על שם יעקב פנטו. וחוץ מזה צריך לחלוק את הקרדיט על כל הפרס הזה להרבה אנשים שהיו חלק מהמחקר. דבר ראשון נדב דנס מהמכון הגיאולוגי, הוא מנחה אחד, הוא הציע את הנושא הזה, הציע את המחקר, ליווה אותו בכל שלב ושלב, וזהו, אז המון נקודה נהדר. וליהודה, שהוא היה ככה קצת יותר מרחוק, אבל עדיין יש לו תרומה מאוד חשובה, נקרא לזה בהוצאה לאור, ובאיך אנחנו מנסים להדגיש את המשמעות של המחקר הזה במקומות אחרים. ניסיתי לעשות חישוב כמה זמן לקח המחקר הזה, אז בערך בין, תלוי איך מגדירים עבודה על המחקר, אבל בין 80 ל-100 ימי שדה, זה מה שנדרש בשביל סך התוצאות שמהוות את הבסיס למחקר הזה, וזה הרבה תודות לכמה אנשים, או להרבה אנשים. יש צוות מחקרי המוח במכון הגיאולוגי, עלי ארנון, שהמון מהרקע הלימנולוגי למדתי ממנה, עלי ליצקי, רענן בוצן ועוד רבים אחרים, חלק מהם יושבים פה, שעשו איתנו בקבוצה, וכל יום שדה כזה, וכל קמפיין כזה, אני לא עושה אותו לבד, אז לאנשים האלה מגיע המון תודה, וגם לאנשים פה במכון, בין אם זה סטודנטים ועוד שמהווים את הסביבה שבתוכה אני פועל ועושה את מה שאני עושה, וגם להם מגיע תודה, רק על אפילו מה שקיים פה. ודבר אחרון, אני רוצה להגיד שזה האנשים שבאופן ישיר נוגעים למחקר, אבל גם כל מורי המכון, ודברים שאנחנו לומדים בקורסים שלנו, החל מהתואר הראשון ועד היום, זה אומנם תרומה שהיא עקיפה, אבל היא מאוד מאוד חשובה, כדי שאנחנו נוכל לעשות את מה שאנחנו עושים. אז גם להם כיף תודה, וכולם תודה רבה.
על בנטור עצמו, תדבר היום נירה ברמטוס. אם אני לא יודע, אחת הסטודנטיות האחרונות.
כן, אחת מהארבעה. Okay, I will speak in English, so our guest will appreciate Bentor as well. So, do you hear me at the back? I'm very happy to speak about Professor Bentor. Bentor was one of my teacher, one of my great teacher, and he was one of my MSc supervisor with Professor Kolodny. Bentor was born as Kurt Winter in 910 in Königsberg, then Germany. In 1933, he immigrated to Israel and changed his name. In Israel, he joined Professor Leo Picard, who sent him to study the volcanic rock of Massif Central. When the Second War broke out, Bentor was arrested in Germany as a spy. He was arrested and was considered as a German spy, but managed to get back to Israel. And in 1945, he received his doctorate in geology on dolomite in Israel, and eventually received his second PhD with distinction from the Sorbonne in 1953. He became an associate professor in 1957. He was active in the Haganah, and Professor Dostrovsky made him part of the Chel HaMadà science arm, and together with Dr. Akiva Frugman, they mapped the southern Negev and found the main economic ores of copper and phosphates, although the original idea was to find oil and uranium. The first map of the Arava Valley was published in 1957, and in 1960 they mapped the Sedom map. The mapping of the Negev is the basis for our understanding of the geology of Israel, and this mapping continues today. For the mapping and discovery of ores, they both received the Israel Prize in 1955 in life sciences at that time. In 1954, Bentor became the head of the Geological Survey, and soon after became the first head of the newly formed Geology Department at the Hebrew University. In this role, he modernized the geological sciences in Israel, recognizing the importance of chemical analysis, X-ray diffraction, radiometric dating, and he introduced this discipline. Bentor is the father of modern geological sciences in the country, and he guided almost all the teachers that we had. Following his retirement in 1977, he left Israel and moved to Scripps Institute of Oceanography. We are lucky that his wife, Professor Miriam Kastner, donates the prize in his name every year, which gives the possibility for us to remember his great contribution to the geological sciences in Israel. Thank you, Miriam. Bentor passed away in 2002, and his legacy is still with us, and I will give some examples. In 1960, when Bentor made the Hatruri information, he divided it to a stratigraphic subunit. I talked with Avi Burg, and according to Avi, who remapped this formation about 30 years later, the original stratigraphy still holds today. He was the first to realize that if Hatruri formation is a combustion metamorphism, there should be a mineralogical evidence. Together with Lisa Eller-Kalai and Shulamit Gross, they published 2 papers in Nature and American Mineralogist demonstrating that indeed the mineralogical assemblage is of very low P and high T. Shulamit Gross continued her great mineralogical studies, finding new chromium clay mineral of the Etringib group and called it bentorite. Many other studies continued after Bentor and continue these days. A subject that was very close to Bentor is the development of the Arabo-Nubian Massif. For us as students, we cannot forget the exciting field trips to the southern Israel and Sinai Desert. His enthusiasm made the rock coming alive. Bentor research started before plate tectonic was fully accepted. He summarized the development of the massif in 75-page long paper in Precambrian research in 1985 after he retired, and in a 500-page book written with his friend and collaborator in Sinai, Moshe Eyal, The Geology of Southern Sinai, Jebel Sabach Sheet, published in 1987. In the Precambrian research paper, he reviewed, that's only Bender can do, he reviewed more than 240 papers that were published since 1900. As an excellent field geologist with a deep understanding of the meaning of chemical analysis, with the new dating just coming out in the late 70s, Bender made huge synthesis of the evolution of the Arabo-Nubian Massif. He identified 4 stages of development: the oceanic Soleitic stage, starting 1,000 million years, the 950 to 650 million year stage with andesitic volcanism and diuretic intrusion, with the chemical characteristic of island arcs, but which he found difficult to reconcile with an island arc system because of the non-linear arrangement and the low-grade metamorphism. The cratonization and stabilization of the massif occurred during the 3rd phase between 640 and 590, a stage that characterized by plutonic granite that outcropped throughout the massif. This phase terminated with a strong uplift. Bender concluded that this 3rd widespread event represented continental collusion events when the Arabo-Nubian Massif and the African Craton sutured together. The last stage between 590 and 550 was an alkaline magmatic phase that affected the entire massif, which is one of the largest igneous provinces. While preparing this introduction, I talked with Dov Avigad on the influence of the plate tectonic on Bender studies. It is clear that he doesn't describe the development of the massif in simple terms of plate tectonics because the criteria did not fully match. Nevertheless, it is clear that Bender wrote a comprehensive review, deep, wide in area and knowledge, and his ability to synthesize large-scale processes was unique. Bender's discussion on geodynamics, origin of magma, processes that led to such wide distribution of volcanism, uplift, and erosion continued by students and by young scientists today. And finally, in connection with this year's Bender Prize, the prize that was given to Ido Sirota for his studies of active salt deposit in the bottom of the Dead Sea and the implication of past deposit in the Dead Sea to other evaporitic basins worldwide, it is nice to remember that Bender published 3 papers, one in 1961. It's true that his idea about the origin of the salt of the Dead Sea differ from what we know today, but he gave very important contribution to some of the geochemical aspects of the Dead Sea and the question of its age, and a manuscript in 1968 on salt deposit of the Dead Sea, and in 1969 on the evolution of the subsurface brines in Israel. So this year we see again that Bender studies indeed inspired many researchers, and we are continued today by a young, bright generation of scientists. I would like also to conclude and emphasize that Bender was a man of great knowledge, not just in geology. He was a man of big and great knowledge in other fields like history, literature, art, and much more. So I will finish in this word and I will let the lecture go on. Thank you.
I'm honored to introduce our lecturer today, Dr. Richard Carlson. Dr. Carlson graduated from Scripps Institution of Oceanography in 1980, then joined the Carnegie Institute as a postdoc and has been there ever since. For the past 4 years, He is the director of the Department of Terrestrial Magnetism at Harvard. Dr. Carlson is a distinguished scientist in isotope geochemistry. Among his many achievements, he was distinguished lecturer of the Mineralogical Society of America between 1915 and 1916, and was awarded the Arthur Day Medal of the Geological Society of America in 2015. Made a mistake? Okay. Another mistake? Before we start, just want to announce that tomorrow Dr. Carlson will give a talk entitled The Nature of Earth's First Crust at 10 o'clock in room 101. And at 11 o'clock, Sonia Esperanza will give a talk titled Effective Proposal Preparation, Perspectives from a NSF Program Officer. Now I invite Dr. Carlson to give his talk, The History of Earth Formation.
Well, thank you for the invitation to be here today. I have to tell you what an honor it is for me in particular. I had the privilege of knowing Dr. Bentor when he was at Scripps, when I was a student there in the 70s. And I think the summary of his career just says what an incredible person he was. And even as a young student there, it was clear that he was a personality that has to be remembered and clearly would make an impact. The other connection here is that Miriam Castor taught me Mineralogy 101 when I was an undergraduate. And I have to say, Miriam, it's one of the courses, one of those courses that you think you're not going to use in the future, but it actually has provided a fundamental understanding that served me throughout my career. So I thank you for that. And then the third connection here we have is that my wife, Sonia Esperanza, obtained her master's degree from this very department. So she's come back now after 38 years. And we're sort of celebrating a return to this, and these many connections that it's funny when you're a young student and me meeting Dr. Bentor, you never think that this is going to mature and develop into anything, right? It's just somebody that you meet on the passing winds. But the opportunity to come here and be the Bentor lecturer is a huge privilege and honor for me. So I thank you for that. What I'd like to do today is tell you the story of the history of Earth formation. And it's going to start a little bit before you normally think this story starts. So it starts when the Earth was something like 10 to the 40, 1 micron particles floating around in the solar nebula at temperatures of basically a couple of tens of degrees Kelvin. This is a story that will follow it through in this illustration that we could have taken out of a textbook from when I was a student. But the fun part about this story, and the one that's changed most, is that basically all these stages from this stage where it's basically just dispersed gas and dust in the solar nebula collapsing down until you form a planetary system. We can observe pretty much every single step in this process now, and it's provided a huge improvement both in terms of observing it astronomically, but also in terms of laboratory analysis, which is my specialty, in looking at how these stages go. So here's a good example, the start of this. What you're seeing here are these beautiful pictures. This is the Eagle Nebula. These are Hubble telescope pictures. And what you're seeing is the light that is from forming stars in this region that's being obscured by dust. So what you're seeing is actually the shadow of all the dust in that area. The reason it's illuminated is because when there is this much dust in an area, this is a place where stars are formed. So you need the mass available to form the stars. And that's what you're seeing here is an area where the stars are being formed. Now, this whole story of planet formation has grown tremendously just in the last 20 years after the discovery of the first planet around other solar systems. So this, oh, thank God, this is a movie that isn't working, which is it's much better this way. This is an example of the thousands of planetary systems that were discovered by the Kepler spacecraft just a few years ago. This is our solar system, for example, and in fact, just the inner solar system. And these are not really to scale, but the point of this is that the size of the planets are to scale. So when you look around other planetary systems in just our galaxy, there's every combination that you can imagine. They have a very big planet like our Jupiter that's inside what would be our orbit of Mercury. They have groupings of small planets. Probably the most surprising is that the most abundant planet that's seen is about a mass of 2 to 5 times the mass of the Earth, which is the size of a planet that we just don't have in our solar system. So the story I'm going to tell you today about the formation of the Earth, starting from this point, may be an oddity, and even in terms of planetary evolution. It's pretty clear that other planetary systems developed other ways to form planets that resulted in very different outcomes. So I'd like to take you back to the start of the story, and that's how you get these molecular clouds to condense in the first place. This is one of these terminology things, is to an astronomer, a dense molecular cloud, this is what they call them, but a dense molecular cloud has a density of 10 to the minus 18 grams per centimeter. So the best vacuum I can get in my mass spectrometer is about 10 to the minus 15. So in other words, these dense molecular clouds are better vacuum than my mass spectrometer by several orders of magnitude. But that's still a lot of material, and the galaxy is a very huge place, and it's still a lot of mass involved in there. So if I can get this running, what this is an animation from one of my colleagues, Alan Boss. That wave going through is the wave emitted from a shock wave from a supernova exploding. Here's a good example of a supernova. This is a star exploding and it's blowing this material out into this galaxy around it. What you see here then is this was a molecular cloud. It's being basically disrupted and torn apart by this shock wave from the supernova. And this is a continuing story in planet formation. So our sun actually is formed from the remnants. It's a very small percentage of the remnants of this molecular cloud that you can see is condensing. If you watch this, this is the density scale. So there's a little point at the beginning of this that's actually being compressed by this all the outflow from the supernova. Most of the molecular cloud is actually just being torn apart and dispersed back into space, but there's a small component of it here that's getting compressed at the top here, and this is what is eventually going to condense to form a star and a planetary system around it. So when this ends, you're at a density of 10 to the minus 12, so you've gained at least 6 to 8 orders of magnitude in density, and by the time you've reached this density, there's enough gravitational potential left in that material where it continues to collapse on its own, just on the basis of its own weight. So you don't need a supernova to do this. There are other ways that you can collect material in the galaxy to get it to these kind of densities. But this is an intriguing way to do it. It suggests that our solar system might have been started because of an exploding star in the nearby system. One thing that supernovas also get for you, it's getting to the area of my research, is these little grains are called presolar grains. So these are grains of very refractory minerals, silicon carbide, for example, graphite, and if in the middle of this graphite grain there's a titanium carbide grain. Titanium nitride is another phase. So they're very strange phases for us thinking in terms of the mineralogy of the Earth, but these are very high temperature condensates that are the things that are forming in the flow of gas that's leaving the star. So these start out as gas when the star explodes, and as it goes away and starts cooling down, you form these grains. We know that they're not from our solar system on the basis of plots like this one. I know many of you are used to seeing oxygen isotopic composition plots where you're seeing delta notations. This is not delta notations. This is the raw ratio, and it's over 5 orders of magnitude. So you don't need much precision to measure these isotopic ratios, but the compensating factor is that these grains are not very big. So the typical grain is about a micron or a few hundred nanometers in size. So we measure most of these using the ion probe, where you can measure these very small sample sizes, not to great precision, but when you have ranges in isotopic composition like this, you don't need great precision. So here is the solar composition. So this is the point. Basically, everything that you would measure on Earth is smaller than one of the dots on this figure, and you can see that these expand out in all sorts of different directions. The different directions that they go tell you about the type of star and the type of stellar process that was producing these grains. So that's an interesting aspect from in terms of nuclear astrophysics, but the important aspect for this story is that these are actually grains that are found in meteorites in our solar system. So in fact, in primitive meteorites, these grains are found at the abundance of a few parts per million, up to 5 or 10 parts per million. So they're rare, but they're not that rare. So they show us, first off, basically our stardust history in our planetary system. And they also show us that not everything that was sitting around in the molecular cloud got destroyed in the process of planet formation. So we still find these in meteorites. These isotope variations are extreme, but what we've been working on in particular is when you move out to the whole meteorite scale, so you're looking at the size of an object that's probably tens of kilometers in diameter, you still see isotopic anomalies that are related to the processes that create the elements in the star. So here's some examples. This is titanium versus chromium. Epsilon is parameters like delta oxygen. It's just 10 to the 4 instead of 10 to the 3, so it's a ratio relative to some standard. These aren't too critical, but the most important point here is that if you look on a diagram like this, the Earth lies in a spot about here. Carbonaceous chondrites is one type of meteorite plot well away from this composition. Other types of meteorites here, ordinary chondrites, and differentiated meteorites, which I'll describe in more detail later, plot down here. So in a plot like this of titanium versus chromium, you could imagine that the Earth is a mixture of carbonaceous chondrites and some meteorites down here that end you up with this bulk composition that we have for the Earth. In some other isotopes, so this is ruthenium versus molybdenum, for example, you see that the Earth lies up at this point here, and basically all types of meteorites lie down in this direction from the Earth point line. There's 1AB is a type of iron meteorite. Carbonaceous chondrites in particular lie way down here. So we're facing this interesting question now is we have finally been able, this is work that's probably only a decade old, we're able now to resolve the fact that the solar nebula, so the region from which the planetary system was forming, was not isotopically homogeneous. So what we're trying to do now is to translate these isotopic heterogeneities, so the differences in the material in the nebula, and how that translates into the composition of the planets that are formed in the nebula. So that'll be part of the story later on. The other nice contribution for my field in particular from a supernova is it makes all sorts of radioactive isotopes, many of which have very short half-lives. So here's a list of isotope systems that have half-lives that are useful for understanding the early history of the solar system, ranging from the decay of aluminum-26 to magnesium-26 with a half-life of only 730,000 years. Up to one that I've been doing a lot of work in, 146 samarium decays to 142 neodymium. Half-life shows 68 here, it's actually 103 now. The 68, I think, is an incorrect new half-life for it. But the point being is that you're looking at half-lives here that are in the 1 million to 100 million year range. And it turns out this is an extremely useful time period because the ability of a chronometer to define precise time depends on its half-life. So the shorter the half-life, the more precise that you can get in its timing. The trouble with this is, of course, is that these were produced 4.5 billion years ago when our solar system started, so none of these exist today. So all we're going to look at is the remnants of them that were present when the planets were forming. These have been extremely useful in terms of refining the age of our solar system, so we know this quite well now, because if you look at a meteorite, this is a particular type of carbonaceous chondrite. It's a very primitive rock. It's basically, if you want to think about it, it's like a solar nebula sediment. So it's got these little objects here, the chondrules. These are little melt droplets of material that was melted as drops in the solar nebula. They're spherical because they were basically floating in free space and they were melted. It has these objects, these white objects, known as calcium aluminum rich inclusions. The importance of that is that calcium and aluminum phases in these, they're oxides and silicates. These are very high temperature condensates. So these are probably the first things to form in our solar system, these little calcium aluminum rich inclusions. And then the black stuff in the middle here is basically the matrix or that cements all this together when this came together as some sort of a cosmic sediment. The beauty of this is that these have rather extreme chemical compositions, so we can actually date the formation quite well. So the lead age now for the calcium aluminum rich inclusions is 4,567.6 plus or minus 0.4. So the argument on this now is definitely in this last place. So we know the age of the solar system to within the nearest couple 100,000 years. So this is always funny when, I know when you've taught Geology 101, you say the Earth is about 4.5 billion years. Well, it's not about 4.5 billion years, it's 4.567.4 billion years. So we know what we're doing in this. Then the dating of these chondrules, ages range, there's actually about a 2 to 3 million year age range in these. They range from almost the same age to ages that are about 3 million years younger or so. So the reason for looking at carbonaceous chondrites in particular is that they've managed to capture the composition of the sun. So the sun is 99.9% of the mass of the solar system. So the average composition of the sun is the average composition of what the whole nebula was at the time. If you look at these meteorites, this is a particularly primitive one. It's called a CI chondrite. This is the Erguet meteorite fell in France. And you compare its composition relative to the sun. So this is the sun's composition as deduced by photometry. So you basically do optical spectroscopy on the sun to determine its composition. And this is a plot relative to the composition of the CI meteorite. Basically everything is the same composition in the CI as it is in the sun, with some exceptions. So carbon and nitrogen are very enriched in the sun, so these very volatile elements, carbon, nitrogen. What's not shown on this is hydrogen and helium, which is several orders of magnitude enriched in the sun. So these are deficient in those elements. the meteorite's deficient, or the sun, sorry, is deficient in lithium, and that's because the lithium is burnt up during nuclear fusion in the sun. And then you see one element here. This turns out, I think it's indium, and what this is it turns out the decimal point is misplaced in the table from which this comes. So this is a good way to see the composition of these meteorites. Know the composition of the sun so well that you can find errors in tables and papers that you edited. So this is from Palmer and O'Neill. I was the editor of this paper and missed this when we were reading through it. So the wisdom for probably 30 or 40 years then has used these type of meteorites as a starting point for the composition of the Earth, because this is the average composition of our solar system, and the Earth is a big place, so it probably represents that composition. But in fact, it doesn't represent that composition very well at all. So this is an interesting plot. It came out of the work from the Messenger mission to Mercury, which was run by my predecessor, Sean Solomon, as chief scientist. This was the satellite that went and orbited Mercury for several years, and it measured the composition of Mercury's surface. So this is a plot of potassium versus thorium. The reason for making a plot like this is you can measure these two elements from space because they're both radioactive, and you can measure the gamma rays that are emitted from your orbiting spacecraft. The other reason for making this plot is that potassium is known as a moderately volatile element. So meaning its temperature condensation, something like 1,000 degrees Kelvin, whereas thorium is a very refractory element that condenses at 1,600 degrees. So you don't normally think of potassium as a volatile element, but in terms of cosmochemical reasons, it is. So what you're seeing here is that these are measurements from Mars, from orbit, has a potassium-thorium ratio of about 5,500. Mercury falls along that line quite well. The Earth is a little bit displaced from it. It's more around 3,000 or so. And then you see here the Moon in particular has a very low potassium-thorium ratio. So the Moon is very highly depleted and volatile relative to all these objects. There's also a Venus data point here, and here. These are the measurements that were made by the Russian Venera lander a long time ago. So we don't have a very good picture of the Venusian surface, but the picture we have also suggests that it's volatile depleted. It's volatile depleted because the solar potassium-thorium ratio is something like 18,000, and yet the potassium-thorium ratio for all the terrestrial planets is only like 5,000. So what you're looking at here is one of the primary chemical features of the terrestrial planets. They're very depleted in even moderately volatile elements like potassium, but also many other elements. So this is a plot that was made popular, in particular by Bill McDonough. What you do here is you plot the elements, this old periodic table, versus the temperature which half of them would condense from a condensing solar nebula. So the refractory elements here, all the elements at very high temperature, plot here basically at the same composition as solar. They show no fractionation relative to one another. And then as you get to the elements that condense at lower temperature here, you run down this correlation here until you've got very depleted compositions. The open squares here are elements that are siderophiles, so these are elements that are soluble in iron and metal, and they've been extracted into the Earth's core. So that's another story. I'm not going to touch on that much today. But the important thing about this is within these elements here, there's a variety of radioactive elements that we can use to date when this volatile depletion occurred. So we do rubidium with strontium, for example. Rubidium moderately volatile, strontium very refractory, and we can do manganese to chromium. Manganese has manganese 53 has a half-life of 3.5 million years, so it's a very sensitive chronometer for very early differentiation events. And it turns out that when you apply these systems, we know that this volatile depletion of the Earth, this is Earth composition, this volatile depletion occurred within 3 million years of the beginning of solar system formation. In fact, it's 3 million all the way back to zero. So in essence, it looks like the planets formed volatile depleted. If they didn't form volatile depleted, it happened very early. So one way is they simply didn't condense all these materials from the nebula. The other way is that they experienced an early high temperature event. So this is not an asteroidal melt, right? This is Hawaii. But you think about this is an asteroidal melt. So this is a type of meteorite known as an angrite. There's a whole class of different, there's actually about 3 different classes of meteorites that represent lava flows onto the surface of asteroids. So with these, you can, since they're igneous rocks, you can date the formation of this very precisely. And here you see all the systems. So uranium-lead is the long-lived system that gives you the absolute age. And then you can do relative ages to this age for manganese, chromium, hafnium, tungsten, aluminum, magnesium. Again, these are the short-lived systems. And you can see you're getting down to incredible temporal resolutions, down to 250,000 years with the uranium lead system here. And all of these are within about 3 to 4 million years of the beginning of solar system history. So what's clear now is that the planets formed very quickly, where that means hundreds of thousands of years, and they had enough heat in them where they melted and produced this type of igneous rock on their surface. If we take that further, we can look at when they formed their cores. So this is I just love this picture of a palisite meteorite. It's iron metal here, olivine grains in the middle. So this represents something like the core mantle boundary of some asteroid. The beauty of this is that with the hafnium tungsten system, it turns out that hafnium 182 decays to tungsten 182 with a 9 million year half-life. Tungsten is siderophile, so it goes into the core when the core forms, or when the metal forms, but hafnium is completely lithophile, meaning it doesn't go into the core at all. So if you start out with a chondrite that has a hafnium-tungsten ratio of something near 1, when the metal forms, it has a hafnium-tungsten ratio of 0, and it leaves behind a mantle that will have a much higher hafnium-tungsten ratio, in this case 10. This is a model for the Earth. This depends on the mass balance between these two, but these numbers are for the Earth. So the interesting aspect of this is that if this happened when 182 hafnium was still alive, your mantle is going to end up with a higher 182 tungsten abundance because this hafnium is going to decay to the tungsten. And if you form the metal early, then this tungsten is going to be depleted in 182 hafnium because, or 182 tungsten because there's no 182 hafnium in the metal. So this has been a particularly useful tool in terms of dating the formation of iron meteorites in particular. So this is work that's done by the group at Munster, Kruger et al., and also with Rich Walker at the University of Maryland. This is the age relative to the age of calcium aluminum-rich inclusions. So the starting point of the solar system. These are different types of iron meteorites. That part's not so important, but the important part here is that you see the scale only goes up to 3 million years. So these things are forming very quickly, these cores of planets forming very quickly in the solar nebula. The model lines here are the lines that you would expect if you start with a chondritic meteorite and you're heating it because of the decay of aluminum-26. So remember, aluminum-26 has a half-life of 730,000 years. It's a rare isotope of aluminum, but aluminum is a major element in planets, and the decay is very energetic. So this is a very easy way to heat planets if they form fast enough that aluminum-26 is still around. So these are the kind of time periods that you need to form a planetesimal big enough to undergo these melting events, something like 100,000 to 600,000 years. So this again is confirming evidence that this sort of diffuse dust and gas mixture got together to form hundreds of kilometer diameter planetesimals within a few 100,000 years. And those bodies were big enough. If they got big enough, they also underwent magnetism, separated a core, and probably erupted lavas onto their surface. So what we have to start thinking about is that maybe the Earth didn't form out of things like this. This is that CI meteorite, the Orgay meteorite, but they instead formed out of something like this. This is the asteroid Vesta. Vesta is an object that's covered in lava flows. We have meteorites from this that are known as HED or Howardite, Eucrite, Dodgenite terminology in meteorites. It's not my fault. Don't blame me. But the point is, it's a differentiated object. It has a core. It has lava flows on the surface. And the interesting aspect then is that this could have undergone a lot of chemical differentiation compared to this. And if our planet started with this, maybe this is the reason that our planet is depleted in volatile elements, rather than having to start with this and come up with some hypothetical process to deplete the Earth in volatile elements. So if you look at the planets in our solar system, these are just the terrestrial planets, you see that even our solar system came out with 5 planets that have 5 very different compositions. So they're different in the degree of volatile depletion, with the Earth being more volatile depleted than the others, but not by that much. They're very different in iron-silicon ratios. I'll show you in a second. The oxidation state is different. Mercury seems to be a very reduced planet. The Earth actually seems to be quite oxidized. The atmospheric history is different. Venus has a almost pure CO2 atmosphere that's very dense, and hence the greenhouse gas properties of that lead the surface temperatures to be several hundred degrees centigrade, like 500 degrees centigrade, whereas the Earth has a water and nitrogen-rich atmosphere and keeps it the climate that we know. And then the properties, the geologic properties of them, allow them to have either continuing geological activity or they were dead early. For example, on the moon, it looks like most of the magmatic activity stopped about 3 billion years ago. There may be younger activity, but it's very small in volume. So let's touch first on this iron-silicon ratio. So this is a ratio of atomic iron to silicon. So this is not the oxidation state. It doesn't care about the oxidation state of iron. It's simply the total amount of iron. And you see this yellow band is the solar ratio. So you see that many types of meteorites lie within the solar range. There are some types of meteorites, though, that seem to be deficient in iron relative to silicon. Venus and the Earth seem to be a little bit enriched. I'm not sure we have the precision to tell that from the yellow band, but they may be a little bit enriched. But then you have Mercury up here that seems to be very enriched in iron, and in contrast, the Moon that's very depleted in iron. So, I mean, these are huge effects. It's a log scale. So you're looking at huge separations of iron to silicate. The easiest way to do that is to separate metal from silicate. And one way that you can do that is when you take account of the way that planets are formed. So this is work from Eric Ausfag. You're looking at the physics of collisions. So each one of these panels here represents a collision between two objects. The red is the core of the object. The blue is the silicate mantle around them. These are some of the outcomes that you can get during a planet collision, whether it's sort of hits off to the top, whether it comes in very, very strongly. You get different results. In this case, the planet actually, this is a hit and run, basically, so the planet disrupts both planets, but this guy will reform and go on wherever it's going to go, but a lot of this mantle material will actually be recollected to the bigger object. So this is one way that you can get an object that's deficient in iron and then one that's enriched in iron. And the same sort of story here. This one is a smaller one. It's basically completely disrupted by the collision. You see the metal here is gravitationally attracted to a large object, so that all ends up streaming back into this object, and then all this material goes back out in space and may recollect to form basically a silicate-free object, metal-free object. And if you remember the plot of the Moon's iron to silicon ratio, this is the way that we think the Moon formed. So I have to show these. You've probably seen these before, but these are so much fun. These are models of the collision of an object with the Earth. So that was the object. It's torn apart. This is the Moon, or this is the Earth heated up. Here's another one that's going to start. This is in the core and mantle. This is from Rob McCanup. This is from Sarah Stewart's group. And you don't want to be on the Earth on this day, right? So this is what happens to it. So these are incredibly energetic events. They're probably typical of planet formation, at least during the latter stages of it. And they can obviously introduce huge amounts of energy. This one was scaled in temperature. So you see here the center temperatures are in the several thousand degrees Kelvin. So this would definitely basically totally melt the planet. Here you see this is the planet's now circular. This is 24 hours. So this is an area, this is hot vaporized gas. And then this is the stuff that's outside that orbit that is where the Moon is going to form. So the Moon probably formed out of this material that was ejected during one of these impacts. And we can look then at the consequences of that by looking at the Moon. So I make the point that there's huge amounts of energy input into the planet this time. If you've got the planet totally molten, you could think about it crystallizing from this molten state. So you think on the Earth, we have the examples of large layered mafic intrusions, Skaregard, the Bushveld. These, you probably heard these in your beginning igneous petrology classes. So the Moon was basically a large layered igneous body. So the thought is that you melted either a large portion of it or all the Moon. The dense minerals, the iron magnesium rich minerals like olivine and pyroxene, sank into the mantle. When that ended the magma getting rich in iron, so it was becoming denser, the liquid was becoming denser, and then you eventually saturate in plagioclase. At that point, the plagioclase actually is less dense than the melt, so it floats. So you basically end up with rockbergs floating above a residual layer here, and this residual layer is enriched in elements that don't fit into olivine, pyroxene, or plagioclase. On the Moon, this is called crete because it's enriched in potassium, rare earth elements, and phosphorus. So this is a nice cartoon model. The question is it real? And if it is real, when did it happen? So if you look at these are chondrite normalized incompatible elements, more incompatible at this end than at this end. And you see the patterns for these various units. So the mantle doesn't like any of these elements in particular, so it's here at fairly low concentration. So there's a little bit higher abundances at this end. Plagioclase rich crust doesn't like any of these elements in particular either, so it's low as well. The one that it does like is europium, because on the Moon in particular, europium is in the +2 oxidation state instead of +3. So it substitutes for calcium in these pelagic clays, and it comes up here. Miriam, that's there. So there's my mineralogy connection with Miriam's class. So this is a substitution for europium for calcium in the pelagic clay structure. And then what you're left over with then, as the liquid evolves, you end up with this liquid that's very enriched in these elements because it's not taken away by the minerals, but it's very deficient in europium here. That's because that europium is in the pelagic clays rich crust. It's also very deficient in potassium, but it's not deficient in potassium because potassium went into these minerals. It's deficient in potassium because the moon is very volatile depleted. So potassium was lost during this impact, and if you looked at the models, the two previous animations I showed you, these are temperatures of thousands of degrees Kelvin, and you basically just evaporated the potassium away. So that's why you've got this well here. So I've tried to convince you that a lot of this activity occurs very early in planetary systems. So let's look at when this separation of the moon and these layers form. So we can do this in a couple ways. One is we can actually go to the rocks from the lunar crust. So these are two different types of lunar crustal rocks, magnesian, sweet, and ferronorthites. You don't need to worry too much about the character of those for this talk at least. They show a fairly wide age range, from 4567 down to about 4200 million years. That's much longer than you would expect if these fractionated from a single crystallizing magma ocean, because such a magma ocean should only last for hundreds of thousands, maybe a couple million years on the moon. But what we've been doing lately is going back to these rocks and using improved techniques to refine the ages down to these red dots here. And you see that they're all sort of collapsing to this age. It's about 4.36 billion years ago. The other interesting thing that you can do is you can do short-lived isotope systems on lunar rocks. So this is 142, 144 neodymium relative to samarium-neodymium ratio. You're probably more familiar, if you're familiar with radiogenic isotopes at all, with the long-lived samarium-neodymium system. 147 samarium decays to 143 neodymium with a 100 billion year half-life. So it's still around, it's decaying, and we use it for many geological studies. This is a short-lived one. This has a 100 million year half-life, so 146 samarium no longer exists. So you can't plot it in the x-axis because it's not there. So you take an analog, 144 samarium, which is a stable isotope. So what's plotted on this are basically every type of lunar rock that we can measure, from Mare basalts here, different compositions, high titanium Mare basalts, low titanium Mare basalts, 3 different types of crustal rocks, and an estimates for the bulk moon here. And the important point is that these kind of fall along a line. I'm not going to call it defined by a line, the data scatter a bit, but you see this is the age of the solar system here at 4.57 billion years. They don't do a very good job of falling on that line. What they do is fall along this line here. It's about 4.35 billion years. And if you look back to these crustal ages, that's about the age that we get for those as well. So what you're looking at here is basically the whole moon is recording an event at something like 4.35 billion years ago. From the formation of its crust to the formation of its deepest interior, which that interior served as the sources of the Mare basalts. So this is kind of exactly the chronological result we would expect if this major differentiation of the moon occurred in a single step very early in its history, where early in this case means 4.36 billion years ago. And that, of course, is exactly what you expect in an energetic impact like this. So if we think about the moon, so the moon is forming out this stuff that's blasting off of this object. But what is the consequence of this on the Earth? You saw in Robert Canuck's illustration that this impact raises the temperature of the Earth to several thousand degrees. So again, we would expect that the Earth would be very highly molten and could maybe differentiate in the same layered nature as the moon did. When we look at the Earth, though, we don't really find that. So here's a couple of ways to get at the composition of the mantle. This is a plot that came from work of Emil Jagetz and Heinrich Vanke in the 70s, where we plot aluminum-silicon ratio versus magnesium-silicon ratio. And what they found is that if you look at different types of chondrites, enstatite chondrites, ordinary chondrites, carbonaceous chondrites, they define something of a trend on this diagram that we'll call the cosmochemical fractionation trend. This probably reflects the volatility of silicon more than anything else. Whereas when you plot earth rocks, so mantle-derived rocks, this is a group of perditite xenoliths. These are mantle samples that come up in recent volcanism in Mongolia that I've been working on with Dmitry Ianov. You see that these fall on a very different trend, so this terrestrial fractionation line, TF, This represents, in this case, the removal of melts. So you're removing aluminum, it's incompatible, goes out with the melt, and you're left with refractory residues of melting. And in this end, you're looking at the addition of melt. So these would be peroxenites or something like that that have been added to the mantle. But what you see is a lot of these samples actually plot quite near this intersection of these two trends, and this is what Yagutz and all suggested would be a good representation for the bulk composition of the Earth, at least the silicate Earth. So we go to these rocks that plot this very fertile composition, and you end up with these messy diagrams over here, which again is the incompatible element plots. The trouble with this is these are little samples that are contained in a volcanic rock. They can be polluted by the volcanic rock, which is very rich in these elements. So you have to watch out for that. So we reconstruct the composition of the rock from their minerals. So this is the orthopyroxene in the mineral in the zenlith. This is the clinopyroxene in the black squares here. And if you put these back together in the mobile abundance of them, you get these open dots here. And then the colored patterns are actual measured whole rock values. So in many cases, the whole rock values show lots of dispersion at this end of the diagram, and that reflects the fact that you've taken in very small amounts of the host the basalt that carried them out of the mantle. But if you look at these in this reconstructed pattern, you can see it's fairly flat in these elements, and then it sort of decreases down with the most highly incompatible elements. So this is something, again, that you would expect as a residue of partial melting events. So even though the major elements suggest that this is in fact fertile mantle, what you see in the incompatible trace elements is that it's a residue of past partial melting events. So again, it's a differentiated part of the Earth. So we can get this in terms of a global scale. This dates back even to the work of Al Hoffman in the late 70s, for example. We know that the continental crust on average, the granitic rocks, the continental crust, are very enriched in the highly incompatible elements at this end, less so of the elements at the other end of the diagram. So you have a pattern like that. The pattern that I showed you for those Mongolian xenoliths looks a lot like this. Turns out this is also the pattern that's suggested to be the source of mid-ocean ridge basalts. So the global volcanic system that makes mid-ocean ridge basalts has a composition like this. And it turns out that if you put this and this together at a right percentage, you get a fairly flat pattern. So what you're looking at here then is a model that, if you remember the model from the moon, it looks something like that, whereas the creek component of the moon would be in the middle. On the Earth, it's the continental crust that's very enriched in these elements, and that formation of continental crust has removed those elements from this depleted mantle, and then there's some fraction of mantle below it that may not have been affected by that. We don't have that. We can't say really how much this mass balance is. But in the moon, I showed you that this happened at 4.35 billion years ago or so. If you look at, you apply the same sort of techniques to understand when this happened on the Earth. You can go through, you can do model ages for mid-ocean ridge basalt mantle, depends which system you use, but they range from something like 200,000 years to 2 billion years. You can do the average continental crust age for Sumerian-Endymion, for example, is 2 billion years, and if you do the model ages for these Mongolian xenoliths, they're also about 1.8 to 2.9 billion years. I don't think any of these ages are absolutely precise. They're not dating single events. But the important recognition is that these are not 4.35 or 4.55 billion years. These are 2 billion years. So what's significant about 2 billion years? The Earth is 4.5 billion years. If you had a continuous process of crust formation operating over that time scale, divide 4.5 by 2, and you end up with 2.25, which is in the range of these type of model ages. So what you're looking at here is this formation of the continental crust did not occur through an early mag motion because of this moon-forming collision. This happened because of the geological processes that we know that have been operating pretty much over the whole history of the Earth. So what does that mean? That means that this process has been working. It's just due to the internal heat energy of the planet. It's erased a lot of what we would have expected from this early high-temperature evolution. So we have to look at other ways to see if we can decipher this old initial differentiation of the Earth from the continuing activity. And it turns out with this short-lived isotopes that we can. So here's an example of work that's done with the hafnium tungsten system. This is largely work at Rich Walker. Some of it's been done in my lab. But what you're looking at here is the tungsten isotopic composition. This is 182 tungsten relative to 184 tungsten. Mu is that difference. It's like delta or epsilon, except mu is in parts in 10 to the 6. So we're getting down to very, very small isotopic differences here. So the present day bulk Earth lies at 0 here. But you see, if you go back to old rocks, so these are old rocks from the area I'll talk about tomorrow. These are 4.3 billion-year-old rocks from Canada, 4 billion-year-old rocks from Canada, 3.8 billion-year-old rocks from Greenland, 3 billion-year-old rocks from Russia, 3.5 billion-year-old rocks from South Africa. These are also 3.5 billion rocks from South Africa. You see here that these rocks, the majority of them actually have positive values of 182 tungsten. Some have slightly negative. So there's a range in this. The important part about this is you can only create variation in this ratio when 182 hafnium is alive. So that's a 9 million year half-life. So that means that these isotopic variations were created within a few half-lives of tungsten. So these were created within the first, say, 50 million years of Earth history. These are not related to the 2 billion, 4 billion year history of continental crust formation on the Earth. If you go to the modern mantle, so here's an example. This is a work recently from Andy Mundell, very exciting work. These are modern volcanic rocks today from places like Hawaii, Iceland, Samoa. And you see that there's, you also see the problem with the resolution. These are the precision of the data, so you're not seeing beautiful correlations here. So the gray band represents the precision about the standard. What you're seeing is a correlation here between tungsten isotopic composition and helium isotopic composition, another tracer of primordial mantle, because helium-3 is not made by radioactive decay. So what you're seeing here then is evidence in this system for chemical changes that occurred in Earth's mantle while 182 tungsten was still alive. We're working on what these mean. The most likely answer is that I mentioned that hafnium tungsten is useful for dating the time of core formation. So one of the options is that you're starting with the Earth, it's like plus 15 parts per million in tungsten 182. Today you're down to 0, and you have some values that are down to as low as minus 20. It turns out that the core, because the core has a hafnium tungsten ratio of 0, has a mu 182 tungsten of something like minus 300. So it's really extreme. And one way to get these lower values is that these represent some very small amount of chemical exchange with the core, where that really low tungsten isotopic composition in the core has been imprinted on the mantle over Earth history. So the chemical processes causing this may be recent, but the initial separation of that core from the mantle occurred when 182 tungsten, or 182 hafnium was still alive to generate these isotope anomalies. We see similar results in another short-lived isotope. This is the work of Sujay Mukhopadhyay in iodine 129 decays to xenon 129 with a 16 million year half-life. What you're looking at here is an iodine 129-130 ratio. This is just a noble gas abundance ratio at the bottom. Trouble with this system is that most of the noble gases are already in the atmosphere, so you always have an air component down at this end, which is mixing with everything that's erupted on the Earth's surface. So what you're looking at here is a mixing line between the air down here and two components in the mantle. So this is an Iceland mantle source here. These are rare gases measured in Iceland basalts versus a mid-ocean ridge basalt sample here. So this again is measured in the mid-ocean ridge basalt. You see that these are very different in iodine 129 and 130. And again, you can only make these isotopic differences by the decay of iodine 129 and within the half-life of it. So within a few half-lives of it. So let's say again 50 to 100 million years of Earth history, the beginning of Earth history. So again, these are signatures of events that did accompany Earth formation. So I mentioned on the moon that a lot of the evidence that we get for this is based on the samarium 146 to 142 system. That has a 100 million year half-life, so it provides a pretty big time window to look at these early events. But when we look at that on the Earth, this is work that I've been working with my postdocs. We look at modern volcanic rocks here. Tomorrow I'll be talking about the older rocks here. These are old Greenland rocks and northern Canada rocks. These are a variety of young ocean island basalts here. This is Baffin Island. It has the highest helium-3-4 ratio that's been measured in modern rocks. And here's some really high precision work done by our lab manager, Mary Duran, where we're trying to resolve just a few parts per million, a couple parts per million variation. You can decide yourself whether that's resolved or not. I'm not going to claim it is at this stage. But the point is it looks like 142 neodymium in all these rocks that show tungsten variation and iodine variation have exactly the same 142 neodymium to 144 neodymium ratio. So why would this be? So this system, samarium neodymium, is primarily affected by melting, by melt differentiation. These are two rare earth elements. They partition differently during melting. So you're seeing here a system that is not remembering a silicate differentiation event from the early days. So what's going on here? So to get back that, we look at very early in Earth history, and this is kind of a preview of what I'll talk about tomorrow. So we've been working on these old crustal rocks here from northern Canada in particular, and there's been a lot of work done in the Greenland rocks as well. So we look at those and see if we can see evidence for the earliest history. And in fact, we can. So here's an isochron in the 146, 142 system for these rocks from, this is on Hudson's Bay here. I'll describe this in some detail tomorrow. But you see an isochron here that gives you an age of something like 4.3 billion years. So these rocks probably formed on Earth's surface about 4.3 billion years ago. So here we actually have samples of material that were formed in that early stage of Earth evolution. And the interesting thing for the purposes of this talk is that these rocks were erupted underwater. So you see pillow basalts in them. This is what pillow basalts look like when they're 4.3 billion years old. This is what they look like today. So this is the lava flow coming out under the lava basin, forming these pillow basalts because the lava is so quickly cooled by erupting underwater. These lavas also display an odd compositional trend where some of them are completely deficient in calcium. So here's a plot of calcium versus magnesium. And some of these are enriched in magnesium and very, very depleted in calcium. So compositions like this are not magmatic compositions. What these are most similar to are basalts on the seafloor that have been extensively altered by hydrothermal circulation. So that's what this pink rock is. It's a Cummingtonite amphibolite instead of a hornblende amphibolite. That's because all the calcium has been removed from these rocks. So even though these rocks are 4.3 billion years old, they look like they erupted onto an Earth's surface that was within the temperature range that you had liquid water present. We don't know if it's oceans or a lake or something, but it was liquid. Okay, so then we can look at the evidence provided by these old rocks and compare it with the evidence we get from the moon. So these are a variety of ways to estimate. It's like the age of the Earth question, the age of the moon. So this is the age of the oldest rock that we have from Nufwagatuk. It's 4.3 billion years old. I'll show you tomorrow these ages for Greenland. This is the iodine-xenon age of the atmosphere, going back to the age of the Patterson in the 50s. Uranium-lead age of the Earth is something like this. This is the oldest age peak for the ancient zircons from Western Australia. So none of these necessarily date the age of Earth formation. But the interesting thing is they're plotting down here, whereas the age of the solar system is out here. You go to the moon, I mentioned a lot of these before, so the crustal ages are down here at about 4.3 to 4.4 billion years. All these have significant uncertainties in them, but again, none of them are at this age of the solar system. They're all down around this sort of 4.35 to 4.4 billion year range. So what I'd like to leave you with is that, in fact, we are seeing the evidence of this initial differentiation of the Earth by looking at the old rocks and getting these type of sort of global scale differentiation ages. It's clear that the Earth and the Moon shared this initial event at something like 4.4 billion years ago, but on the Earth, that's been largely erased, and you can see that in the neodymium record, actually. So here's a plot of 142 neodymium versus time for old rocks and then to the modern day. You've got a lot of variability in 142 neodymium in these ancient rocks, so this is a result of differentiation when 146 samarium was still alive. So basically around 4.4 and younger ages produce this type of variation. But as you go down in time, for the most part, there's one exception here I'll talk about tomorrow, but this variation decreases until today you have no measurable variation. I think it's still there, it's just we don't have the precisions yet to resolve it. So the most likely way that you erase this variability is that this is a result of the initial differentiation of the Earth, but when you start plate tectonics and you start cycling this sort of layered Earth back together, you convectively stir it back together. You can't create these anomalies anymore, but by mixing something up here with something down here, you can erase the anomaly. So you've basically taken this nicely layered Earth that was left over, it's like the moon, and through mammal convection, you've brought it back down to this value. So that's brought it back down to that value in 142 neodymium, because all the variation in 142 neodymium had to occur back here, but you've created a heterogeneity in the longer lived system. So the strontium isotope heterogeneity, the 143 neodymium isotope heterogeneity, the lead isotopic heterogeneity that we know in the modern mantle is a result of this long-term process of continent formation. But that process doesn't imprint these short-lived isotope systems because the parent is dead. So basically, we're using these short-lived systems to only look at this initial period of Earth evolution, whereas we can use the long-lived systems, which we've been using for 40, 50 years for this purpose, to look at the longer-running geologic history of differentiation of the Earth. So that's the story. I'll leave you with the conclusions here. So the Earth inherited compositional variations that was present in the nebula. This is primarily the volatile depletion, and particularly this isotopic distinction. This is an area that I think will be a particularly important thing in the future because we're having trouble translating these very small isotopic differences to what it means for the bulk composition of the Earth. And that's actually a very interesting question. The main mass of the Earth may derive from early differentiated planetesimals. They became differentiated because they formed quickly and there was enough aluminum-26 around to melt them. This gets interesting if you're thinking about exoplanet systems, so planetary systems around other stars, because the abundance of aluminum-26 in the galaxy is very not uniform. So if you had a planetary system that either took longer to develop or didn't have as much aluminum-26 as our solar system had, you may not have differentiated the planetesimals when they were forming. You could end up with planets that are actually very primitive in composition, basically the same composition as a star. So this is one way that you'd make compositional differences between different solar systems. I would like to leave you with the idea that the Earth and the Moon share a global differentiation event at around this time, 4.4 and not 4.56 billion years ago. I think the best explanation for this is that the giant impact into the Earth that made the Moon happened relatively late in solar system history, where relatively late means 4.4 billion years ago. The accessible Earth, meaning the part that we can sample by volcanism, is slightly depleting these highly incompatible elements, and I think that's best explained by the extraction of continental crust, an idea that's been around for 30 or 40 years. I think increasingly what we're seeing is that crust formation began quickly because we're finding, like the zircons from Australia that are about 4.35 billion years, the 4.3 billion-year-old rocks from Canada. We're seeing that it began quickly, and it was broadly basaltic crust. It was this first characteristic of the crust of the Earth. And so we also see that the Earth was cool enough, so coming down from this giant impact of 4.4, by 4.3 it was cool enough to have liquid water on the surface. So it's not those beautiful artist conceptions of the Earth that you see with magma everywhere, right? Leaking out of cracks over the whole Earth. It probably did look like that, but only looked like that for a few 100,000 to maybe a few million years. By 4.3 billion years ago, it probably looked a little bit like it does now, without the planets, of course. The effect of this initial global differentiation was erased by mantle convection, leaving you with this sort of 2 billion year mean age for both mantle and crustal reservoirs. This is simply a mean age. It's not any single event. It's the fact that you've got a continuous process forming continental crust. And then one of the things that we're working on right now is that this seeking evidence for the remnants of this early differentiation. I showed you in the tungsten and the iodine data that it's there. We don't really know what these are. It could be the core for tungsten. It could be some atmospheric loss thing for iodine. But we're trying to figure out what exactly are the physical causes of these ancient signatures recorded in the isotope system. So, of course, this isn't just my work. This is the list of the people that have contributed to it. Actually, I did most of the work, largely my postdocs and colleagues, and with the financial support that supported a lot of this work. So I thank you for your attention, and I'm happy to answer questions.
Regarding questions, first, everyone wants to leave, can leave now because we have classes. The rest will want to remain for the questions. So questions?
Do you see any evidence for an incomplete separation of the core? I mean, was it a very quick event that took most of the iron out? And was there any iron left, metallic iron left within the mantle from this age?
Well, so they're basically, the best answer to that comes from the group of elements known as the highly acidophile elements. So these are platinum group elements, platinum, iridium, osmium, radium. The answer to that traditionally has been that the core came out, so these are elements that have partition coefficients for the metal that are like 1,000,000 to 1. So basically, core formation, if it were in equilibrium with the mantle, should have completely stripped these elements out of the mantle. They're not completely stripped. They're about a factor of 500 lower than chondritic values rather than 1,000,000 lower. So core formation wasn't complete. The answer, though, is the question of is whether those materials are added later. So there's the late veneer explanation, where you had core formation and took everything, all these elements out of the mantle completely, and then they came in by late additions of chondritic material. And that material didn't mix with the core. But I think an interesting problem that's come up is the other way to get this is that, like you say, you left some fraction of that iron behind in the mantle, and it got oxidized, and we don't recognize it as metal anymore, but it left its chemical signature. That idea, it's called inefficient core formation, was scrapped in the late 70s, early 80s, because it was the argument against it was based on partitioning of those elements with sulfides. So the whole wisdom behind it was that the formation of the core occurred in a marginally molten mantle, where you're just barely getting to the melting point of iron, and that iron was streaming through solid silicates. So you had sulfide was one of the liquidous phases on it, and it would affect the partitioning of these elements. I think we need to revisit that model, because in a giant impact model for the Earth, this was totally molten Earth. So what you're looking at then is simply the raining of the iron through the mantle into the core. If you then left some of that iron behind, so you had even 0.1% of that metal left behind in the mantle, and then you just convectively stir that in, you'd end up with the highly acidophile abundances we have. So I think this is an increasingly likely explanation for it, inefficient core formation, but in a different way than that model was set up in the 70s and 80s. I think one of the other arguments for that is that a lot of the work that Rich Walker and his postdocs have done have looked at this on the Moon and Mars, for example, and they all show this similar abundances of highly acidophile elements that are chondritic relative abundances. And they should be fractionated by iron metal, but they seem to be about the same abundance. So you think about the Moon in particular, we know that the Moon's crust was in place within a few million years of the formation of the Moon. How do you get a late veneer into the lunar mantle if you've got a thick north acidic crust there? So I think the answer is that this late addition idea is having mechanical problems with how you deposit it into the planet. And I think we need to go back and look at the inefficient core formation idea and give it more thought in the modern idea of a high temperature formation for the Earth.
So the question is, what is actually the implication of the last diagram that you showed with the 142 or the 143? And that goes back to the question of the mature mantle, right? So there is an implication, because if there is all this kind of variation in the 142, it implies something for the 143. Now, if there are variations in the 143 and they are erased later as the 142 because of the homogenization, then do we have a mature mantle in the beginning according to the model of the Wasserburg and the Paolo, or it's not a mature mantle?
So this wasn't a plant. Modi and I did not talk about this ahead of time. So this I think is the answer to your question. This is a plot of neodymium isotope data. This is the short-lived system, 142 neodymium, 143 neodymium over here. So this is a long-lived system. And they have to be correlated. They're the same parent to daughter element. The only difference between them is the time period that they record. So the 146 samarium only records the chemistry when it's alive. So what you get here is looking in particular at Greenland. This is before we had a lot of data on the negative side of this. But you're looking at here the idea that you started with a chondritic mantle. We can argue about that, but you started somewhere and you had a differentiation event that made a high samarium to dimming ratio, got you up to here, and then you're mixing that with your chondritic mantle back here to produce this changing values. These are Greenland data, for example. This is an older slide. And if you do that, you have to have the same consequences in 143, and that's what you see here. So going back to the 143 data, there's always been this huge range in 143 initials in ancient rocks. A lot of that is probably noise and the effects of metamorphosis, so that's another time we can argue about. But that's the data, unfiltered data. And if you take the parameters that create those curves, you get that. This is your mixing period, and then this is when you start crust formation to evolve out to mid-ocean ridge salts today. So I think you can reconcile these. So during this interval, so this is the initial differentiation event where you're doing both systems. This is the differentiation event where you're only affecting the 147 to 143 system. And what this is doing to you is mixing away this anomaly to the point that there's none today. So I think you can reconcile the two systems quite well, except you have to be thinking about the windows of time that they're actually recording.
No, that's okay, I understand it. But the question again again, how do you start? Because before you were arguing in the beginning of your talk that we are not like C1 type and something different. So, and then you showed that the Emiliakos diagram, and the Emiliakos diagram is really, it's like we are C1 type or something. But then from here, it's not clear if we are starting with Chur or not starting with Chur. What is your opinion about it?
So Chur is based on the 143 system in particular. It turns out with 142 neodymium, 142 neodymium is one of the isotope systems that shows isotopic variation between different types of chondrites. So there is no Chur for 142 neodymium system.
But there is for 143.
I mean, this is the complication. This is the nucleosynthetic side of the story. So the variations in 142 are small enough where the nucleosynthetic part matters. So we don't really know what the Earth started at 142. We've had a whole series of papers where we say it's not chondritic and work from there. I still think that there's merit in saying that the Earth does not have a chondritic samarium-neodymium ratio. That it is in fact, it's not as high as the modern mid-ocean ridge basalt value, but it would be a value that would produce a range like this. It's like your Momo value or something like that, or what Alan Zindler called prima back in the 70s. So most ocean island basalts have 143 neodymium values in this range. And I think there's reason to think that that actually might represent the primitive mantle, or at least the mantle after the initial differentiation. And that's the mantle that we have today. So I don't think we need to go back to the Chur value as the answer. And then that changes the amount. When I showed you that plot of continental crust plus depleted mantle plus primitive mantle, I'm not sure we need that primitive mantle box to be even there at all, or if it's there at all, it could be quite small.
If I would intriguing that the first rocks that are found were formed already under existing ocean.
Yeah.
And the question is do you think that it is a cause and effect? It is actually related to each other, or they could have been earlier rocks before that could have survived before there were oceans of Earth?
That's a very good question. I think preservation is a big part of the story. So I think what we're seeing in these old rocks is simply what got lucky to survive. What happened before that is there had to be a crust on the Earth after it formed, just by definition. So the question then is, what is the nature of that crust? So if it's a dense basaltic crust, if you think about a magma ocean, on the Earth, you could end up even with like a prototitic crust. So if the whole Earth is molten. So it might have been too dense to survive, and it just was sinking, and then it was being replaced by this type of stuff. I actually think that like the Nouveau Arctic here, I'll describe those rocks in some detail in my talk tomorrow. I think what you're looking at for the earliest crust on the Earth were big basaltic platforms, sort of more like an Iceland type of analog. Whether you need an ocean for them to continue to exist, I'm not sure how it would play into it. One of the things that you probably did need an ocean for is, so if you had a basaltic platform to make granites, in the sense of Toledo, you had to add water to that basalt and remelt it, right? So I think the existence of continental crust owes its origin to the presence of oceans. I'm not so sure that the presence of these big basaltic platforms, these Hadean rocks, necessarily owes its origin to water, but it's a good question. So there's lots of issues about what stabilizes the crust. So the models we don't really know how plate tectonics gets going. One of the ideas is it has to do with the temperature boundary across the surface. So if you had a very hot atmosphere and it kept the surface of the Earth hot, it's possible that you could not get subduction. And then once it cooled down enough where you had liquid water, then you maybe could get subduction in the beginning of the volcanic system that we have today. So I think it's a very good question that we don't have an answer to, but it's something we're thinking about.
I just have a question about homogenization. You can have it by convection or by subduction. Could you distinguish between the two of them? Or when did subduction start? Could you use some of the data to decide when subduction started?
I think subduction started here. But that's just me. I think the answer is that if you perfectly subduct oceanic crust and continental sediments on top of it, it's as though the formation of the oceanic crust never happened. Right? So if you completely homogenize it, you lose that synergy. In terms of distinguishing between subduction of continental crust and oceanic crust, I think you can see that in the modern volcanic record in terms of the chemical characteristics of the oceanic rocks that are erupted from that. We know that in young rocks, for example, there's mass independently fractionated sulfur now showing up. So this is surface sulfur from the Archean that's got in the mantle, wandered around, and came back in a modern volcano. So that is very clearly a signature of subducted crustal components. I think subduction is probably the primary way that you get rid of these signatures. So to me, subduction happened. If you remember, Bob Stern was another of the students who were with us at the time. There was a meeting a few years ago that was exactly addressed to the question, when did plate tectonics begin? They gave out a questionnaire at the beginning, and at the beginning their answers ranged from 800 million to 3.5 billion. And at the end they ranged from 900 million to 4 billion. so it's not clear. And it's a question of whether you use the metamorphic characteristics. So Bob will continually tell you that you need to have blue schist to define subduction. I don't think that's true. I go by the chemical signatures of what looks like an arc rock. We see those. I'll show you tomorrow in these new architect rocks from Greenland. At 3.8 billion years ago, you're producing rocks that look like modern arc rocks. So I think subduction started very early. It may not look the same way as we do now. So if you look at geodynamic models of ancient subduction in a hot mantle, they look more like drips. So the surface plate goes and then it just basically falls off. So you don't get these nice 45-degree dip, long-lived subduction zones. But it's the same process in the end. And once you get that in the mantle, it's just convective stirring.
Last questions?
When we're talking about the beginning of plate tectonics, we usually think it's relevant to tectonics. But actually, one of the results of plate tectonics is cooling of the Earth. So, if we go back enough in time, there was no plate tectonic, and the internal heat generation in the Earth was several times larger than today, then would you expect to have some expression in rock types and spectrum of magmas and so on for higher temperature? And if not, wouldn't that be a clue to the operation of plate tectonic and efficient cooling?
Yeah. I think an even better answer to that question is the generation of magnetic field. So the energy source for the Earth's magnetic field is cooling of the core.
Yeah.
You don't cool the core if the mantle is as hot as the core. So to me, now there's paleomagnetic evidence, a little bit disputed, but there's paleomagnetic evidence for a terrestrial magnetic field that's more or less the same intensity as the current one, back to at least 3 billion, and maybe there's some reports of it in these 4 billion-year-old zircons, but that's questionable. But it's at 3 billion. So the answer is, if plate subduction is essential to cool the mantle, particularly cooling the core. If you think about modern plate subduction, you're taking the cold surface layer and you're putting it right on the outside of the core, right? Perfect way to start cooling the core. So if that is the necessary energy source to drive a dynamo, that to me is a very strong sign of plate subduction. Whereas you look at Venus, Venus has no magnetic field. There's no evidence that it had plate tectonics, though that's disputed. I mean, there are surface features of Venus that look like a modern subduction zone. It's this, the asymmetric thrust fault type of structures. So there are features of that, but it's terribly resolved. But you don't have a magnetic field on Venus. So the alternative is that you have this sort of heat pipe system where basically you've got a big thick crust that's sitting there. The interior of the planet's getting hotter and hotter and hotter until it just boom. And then you get one event that turns over. I think the Earth, the magnetic field, Earth has one, Venus doesn't have one. I think that is a pretty good sign of plate tectonics operating very early on here. It's the cooling of the mantle, I think, is really the key.
So, but you don't see any expression of a major change in the type of, say, the meteorological factor.
You do see a change. You see a very subtle change. Blair Shaney at Princeton and a student, Brian Keller's doing a lot of work on this. Where if you look at all the rocks over Earth history, this actually goes back to Ross Taylor. Rocks in the Archean tend to be more magnesium. So they tend to have higher magnesium. You have commodites, you have higher magnesium basalts. And you do see a transition at about 2.7 million years down to a more modern assembly. And that's almost always interpreted as as a sign of hot or mantle. Mantle had to be hotter in the past. The question is how much. And I think increasingly the difference isn't very much, which again makes me think of seduction as a way to regulate the mantle temperature.
But could you modulate if you just cool the earth by radioactive decay and everything else, and you got it tectonic? Could you calculate when would the magnesium crack?
Well, you can do that. It depends on what you think the initial uranium, thorium, potassium content of the Earth is. This gets back to Modi's question: is if back in the models where we were talking about a non-converting Earth, it's possible that those abundances are a factor of 2 or 3 lower than current estimates. And if they're that low, then you have trouble driving convection, period. So I think the answer is it's very sensitive to the amount of radioactivity you choose. Yeah, so, but it's clear the mantle's been cooling through time, but I think there's still a little bit of debate about how much and what's the mechanism of it.
Okay, thank you. Remind you, tomorrow the talks, Sonia, and to all of us who are interested in MSF, BSF submissions are going on and quite successful, I want to say. You should come and listen to Sonia.
What levels 2.3 something rocks in Canada? This is what indicated when they were getting 142.
The 4.3. Yeah, that's what we're talking about. But, so there's a series of metamorphosis salts in the pretty highly altered too. And if you apply the normal dating systems, there's no zircons in the walls. So if you apply the normal spin, you get 3.8 or something like that. There's flags all around that are as old as 375. Those are nobody's using. If you look at the 146, 142 system, you get to the 4.3 billion isotopes. They've been interpreted as mixing lines between some heating and the 3.8. I don't believe that for a few reasons. One is that it turns out if you do the mixing calculation, the composition of the heating has to be the same composition as the rocks. That's the originating member of the rocks. The other one, there's one of the other arguments that I think is particularly strong is there are ultimately sills within the sequence that differentiate. So there's peroxide, pretty tight in the middle, or tonite basically. And if you do samaritanimic on those, you still see the 4.3 billion isotopes. Those are clearly olivine controlled fractionation trends. Okay, so these are not some mixing. This is a homogeneous batch of active differentiated, and it's controlled by olivine fractionation. Though, if that happened at 3.8, there would be no 142 variation. So it's a big range in samaritanimic ratio. So again, I think that's another sign that this happened while 146 was alive. So there's a few arguments like that, and then there's 3 different compositional groups in that, they all give the same age. So I think the argument's pretty strong. It's not accepted.
You can also explain the 3.8 modulator of the regular scenario, the 147,
for those groups. No, actually 147, 144, the tonalized area here are 4 something. So it's an area, the Hudson's Bay terrain, Hudson's Bay, and then the part that sticks up like this, there's a big section of it that's called the Hudson Bay terrain. It's composed of areas where just the 2-7 granites have native modeling, so they create the 4 billion. And the rock is a little piece of that. So it's a part of the crust that I think everybody agrees is very old. Whether very old means 3.8 or 4.3 is where the debate is. Okay. I think it's 4.3, but there's room for argument. If you're coming tomorrow, you're not coming tomorrow. Yeah. Things being recorded. Hi.
Thank you.
Yeah, pleasure.
I may be out of logic. Thank you.